Hey everyone, I'm Oppo here, and today we're going to show you how to vibe your way towards a board bring up. In this case, we've got a DC to DC converter that I've purchased online, and I want to profile this using vibes only. That means that an agent is going to control all of my equipment here in my lab, power on the board, and then run all sorts of characterization models on it, get efficiency, power it on, test it, put it under load, and evaluate everything for me without me lifting a finger. So get your environment up and running. Join me because you're going to enjoy this one. Let's get started. I'm just going to show you my setup over here. This is the DC to DC converter. As you can see, on the left side, we have the power supply and the channel 1 of the oscilloscopes hooked up. That's the input, and then the output, as you can see over here, this is the channel 2 of the oscilloscope and my electronic load that is hooked up, as you can see right over here. So I've got my electronic load, I've got my power supply, and then I've got my oscilloscope right here. So everything is hooked up. I just want to give you a quick overview of the hardware setup. Pretty simple. We're going to dive into the actual project overview next. Okay, so as we always do, I want to give a little bit of a project overview of what we're trying to do over here. What we have is I have purchased this DC to DC buck converter from Amazon online. And I mean, there are plenty of these different DC to DC converters. The most important thing is I'm using this chip, the LM2596. The LM2596 is really, I think it originally comes from a TI component, and this is the data sheet. So this is a DC to DC switching buck converter. Very simple. It's pretty popular. I believe it's deprecated by this point. Yes, they have a newer version of these components. It's still active, but they have a newer version of these components that they're recommending. So what I did is I got this board over here, or the set of DC to DC converters, and I wanted to, instead of profiling it myself, I wanted to basically give it to an LLM to bring up, to test it, and all of that. Obviously, that's quite a feat. We've been working on a lot of really interesting, different kind of projects over the last couple tutorials to finally get to this point. So as I showed you in the video previously, I have my oscilloscope hooked up to the input and the output of the board, channel 1 and channel 2, and I have the power supply going in and an electronic load going out. So this is like a standard way of testing a DC to DC converter: voltage in, voltage out, start syncing current, and as you ramp up the current, you want to gauge how much voltage drop you have, and then figuring out power in versus power out. And then that tells you the efficiency of the converter. There's other stuff like ripple current, things like that that we want to also measure. But that's the basic gist of testing a DC to DC converter when you're designing one of those, if you recall that from maybe a power electronics course you took in school. So I want to do the same thing, but I don't want to waste my time bringing it up myself. I have clearly too many important things to do. So I would love my agent to take care of that for me. Good news, you're in luck, because we've been building the capability through a few series of repositories and tutorials until now. So first of all, before I even get into the Agentic hardware controllable aspect of this project, I needed to take this data sheet and extract it so that the LLM can consume some information. So in the previous tutorial that I've done recently, we built this datasheet extractor. If you recall, I was on a specific tag tutorial release, and we built this datasheet extractor software that basically, using the Dockling open source library, it extracts all of the text from the LM259 from the PDF, and then it outputs it into some sort of like JSON format. So and JSON and some other stuff. So if I go here, I ran this guy right over here, and I ran it, and then in document.json, I have all of these different like chunks. I have different information about different tables, things like that. As you can see, it's quite a large document. But this is something that's a little bit easier for an LLM to consume versus giving it a PDF. If you give, for example, Claude Code a PDF, it will try to run Py PDF to text or whatever library, or if you give it to an LLM, if you put it in like ChatGPT, it has its own backend engine to process PDFs. This is just a lot cleaner. I can reuse it, simpler, so on and so forth. In this particular case, I did not extract out the images. I wanted to do something super fast, quick and dirty. So the images takes a little bit of a time. You need a locally hosted LLM or cloud hosted LLM for the vision model. I just didn't want to deal with that. So I just took out the text for now. Okay, so that's the datasheet extraction. And that, as you can see, is in this repository, the LM2596 AI-based verification in my public GitHub. All of these repos are in my github.com/amapor. You can find it there. Next, we have 3 MCP servers. We've talked about this before. We've even gone through building these MCP servers before. This one you're probably familiar with, the DP832. We've built this. This is a tutorial we've done. This is Model Context Protocol. I definitely recommend you checking out the tutorial just so you can get an understanding. But these are basically tools that we give to the LLM to essentially say, here you go, like here's how you turn on a power supply, here's how you read current, here's how you set the voltage, blah, blah, blah. Okay, we did this for the Rigol DP832, which I've got over here. We did this with the Rigol DL3021, which is an electronic load. And I forked this repo, thank you very much, TSP, SPI, whoever you are, who put the Pi MSO 5000 library out there. I forked that and threw the MCP on top of that, as you can see right over here. Great. Okay, so now I'm going to close these up. I pull in those MCP tools. I've written various context awareness in my repository, like a Claude MD, so it knows that, hey, these are instruments that I want to use. I also told it how I set up my environment. So channel 2 is on the channel 2 on the power supply is what is driving my DC to DC converter. Channel 1 on the scope is the same as the power supply. It's the input of the device under test, and then scope channel 2 is the output of the device under test. And then the same thing, the electronic load is on the output of the device under test. There are some other kind of like hints and skills and whatever you want to talk about in this document. There's also a README. There's a whole bunch of it. There's the data sheet, all of that. Okay, great. So now we have full context of the data sheet, which we have over here. We have the README, we have our Claude, and this became quite interesting. So I wanted to kind of automate the data ingestion of what this is, what this product is. And so Claude or Cursor or whatever my AI agent Codex, I didn't want to have it constantly go to the web or go to Amazon and try to grab the product description and try to discern from the photos, you know, how the board is designed and all of that. So what I did was I told it, I gave it the link and I said, here's a product description. Actually, I copied the product description from the website over here. I grabbed everything under product description, all of this. So I grabbed that context. I grabbed all of the images over here. And then I said, basically build out, you know, all the product information that's needed. So intelligently, it went and looked at the images and then identified all of the board components. And so immediately when it did that, it said, wait a second, I also looked at your datasheet specs that you put into a document.json and discovered that the TI datasheet recommends that it says that it is 150 kilohertz switching frequency, I guess nominal. I didn't look at the exact details, but yes, here we go. 150 kilohertz switching frequency. But this guy is telling us that it's 65 kilohertz. So that's already a discrepancy. It's saying possibly a clone chip, which for the record, I want to be super clear. This does not call out TI anywhere in the description. If it said this is built on the exact Texas Instruments chip, then I would be a little bit concerned, which I do not see over here. It just says LM 2596. So that was something that the LLM, I think, got a little bit tripped on. It thinks that this is dealing with the exact TI chip, because I wasn't clear about that. Okay, no problem. But it did take the description and it made this like kind of nice product description.md. So as you can see over here, it was able to discern the electrolytic capacitors, the inductor value, which this was cool too. The inductor was marked at 470, but then it went to the data sheet and said, hey, the range for the inductor is 33 to 68 microhenries. So it's not possible that the inductor itself is 470 microhenries. I'll show you the picture. It must be that this is maybe 47.0 or something like that. So it must be that this is 47 microhenries. There's no way that these designers put 470 microhenries on here. That's completely out of scope. I thought that was pretty cool. The deductive reasoning there was pretty neat. And again, because it had free access, very quick access to some of the datasheet information, it was able to like traverse very quickly through that JSON document. Okay, so that's the kind of setup that we have. And we're now going to kind of walk into how we do the agentic stuff. But I wanted to just give you an overview of what we have now, and then we're gonna dive into like the real demo. So when you have all of the MCP capabilities and your hardware hooked up, you kind of have now opened up a whole new world for the agent to start experimenting with things and doing things. So I'm in Cursor right now. I'm using Composer 1.5. I'm actually going to demonstrate this as well with Claude Code. But what I'll do first is, I'll do a one-shot prompt. I won't even tell it anything about the MCP servers. Let's see how good it is. Tell me what Rigol devices I have connected and what their IP addresses are. Okay, let's see if it automatically picks up the MCP tools first. You have to be aware that I have a lot of MCP tools right now. So sometimes the context doesn't really know. And so as you can see over here, there's like a lot of MCP tools. So it can be really hard if you have hundreds and hundreds of MCP tool calls, but it figured it out, which is super nice. And now in parallel with 3 different agents, it is going and running that operation. Turns out that the problem is MCP attempted, but now for some reason it failed. So that means that I probably need to reset my MCP server. So let's do this again. And I think this is because I was using Claude too. So it gets a little tripped up if I'm using multiple instances all running the same MCP server. Let's do this again. Brand new chat. So it has no context of what happened before. Okay, there you go. So now it's calling the MCP server. So I've got discovers and I've also got test connections. Let's see, what does test connection do? Status, success, IP address. And it gives me the ID string, the Skippy command to do the ID query. Cool. Let's see what it just comes back with. Now remember, I'm also using Composer 1.5. So that's not like a flagship model per se. It is a thinking model, but that's nice. Like it automatically is able to figure that out. I bet if I use Composer 1, it can do this too. Pretty menial tasks. So it should be able to do this. Okay, so this is cool. Now I have the IP address. So I can go to the Oscilloscope webpage and here we go. So now I have my oscilloscope up and running. So you can see that it's going to do real things. Okay, so we have that. And let's go into Claude Code. So disconnect from the instruments, please, just to be safe. Okay. We really don't need a fancy model for this. So I'm going to go to Sonnet, I'm going to go to medium effort, and I'm going to say hook up to all my Rigol instruments. Okay. So now it's going to do the same thing that Composer just did. Great. And hooking up to all three simultaneously. Cool. So we can run all those different tools because they're different MCP servers. And then I'll set up my prompt. Given the information you have about this DC to DC converter, read through the docs in this repo. I want you to propose a basic smoke test checkout plan. Keep it short and sweet. People are watching. Okay, so let's see what it proposes. And also keep in mind, look at this bypass permissions on. Also with my cursor, I love to run in YOLO mode. I love vibing. And so this is super dangerous if you don't know what you're doing. So please, please use caution. You could easily blow up stuff. So just be really careful. So I'm going to have it turn on the device and run through it. So let's take a pause here and then set everything up. Okay, so before we move into the datasheet analysis and the actual board product comparison plan that we talked about over here, I just want to report some of the results from the previous run, which was running the actual ripple current. So I can actually run this again, but I'll just show you. So initially I used the Sonnet model, which we used before, and that was not able to calculate and get the ripple current correctly. I then moved to the Opus model, and it's telling me that the ripple current is 27.5 kilohertz. I have to go in there, double check it, manually verify myself. But again, this is more about a red flag warning to say like, hey, this is not what they advertise. Again, is it correct? It's possible that the LLM did it totally wrong. Maybe it didn't understand how to retrieve the ripple current. Maybe the FFT wasn't working correctly, but it did use an FFT. It was able to do the analysis, and then it told me that it was 27.5 kilohertz and the justification for that. So clean harmonic structure at 55 kilohertz, 13.3 millivolts, which is pretty negligible. Same thing, another harmonic at 82.5 kilohertz. So really the only harmonic with a reasonable amplitude of 50 millivolts was 27.5. So that's in terms of the spectrum analysis on the FFT. It was only able to find that first harmonic at 27.5 kilohertz. Now, I mean, again, how well did it capture it? How well was it working? I have to then go manually and double check it, but it says it doesn't even meet the spec. Okay, fine. Not a big deal. I can go manually verify that myself, but at least it told me, hey, be warned about this. The next thing that I ran through, and I'm going to kind of shortcut this because the actual run itself took 14 minutes and 2 seconds. So that was like a long plan that it ran through. So when it first ran this whole project, the agent told me that it wanted to do an analysis. It says, hey, you know what? I'm seeing some kind of like funny things with the product description compared to the datasheet. And I think there are some limitations in terms of how this DC to DC converter should be running if this was from TI. So I would like to put together a plan that kind of does some analysis to look at the datasheet and compare it against the product specs and just see, if it really does meet the spec of the datasheet itself to determine if this is the real TI chip or if this is a counterfeit chip, which in this case, I mean, I know it's not that exact TI chip. The question was from an ASIC standpoint, does the chip, when you advertise LM2596, does it still meet the spec of the original LM2596? That's debatable if you want to call it counterfeit. I don't know if I would go that far to call it counterfeit. If they actually called it a TI LM2596 chip, maybe that would be counterfeit. It nowhere in the description said any mention of TI or called out the TI spec. So I'm not gonna pay credence to what the LLM told me in its report, but it is an interesting exercise, especially if you want to like do some sort of deeper evaluation of chips or boards or things like that. So this was the plan. And again, take it with a grain of salt, because there really was no like tight spec that was called out in the Amazon product description. So I paid very little money for these boards. So I didn't expect a lot coming out. It says, let's, here are all the specs. Here's what TI recommends. This is the source from that document.json, where we retrieved all those specs. So you can go manually verify, meaning it's telling us the source of truth. So it's not, quote, hallucinating, which we used to see all the time in old rags. And so this is the static analysis that we did. And now we're going to do some sort of like measurements. We're going to measure, record the voltage out. We want to look at the efficiency. We want to look at the ripple. We want to look all of that. Okay. And once we do that, we're then going to basically, test that and verify it and all of that stuff. And then we'll generate a report. This is the execution orders. And then in terms of disabling the safety instructions, stuff like that. Again, remember I'm running in YOLO mode. Probably should set your OVPs, OCPs, stuff like that. If you don't have 100% trust in your LLM, which is probably good to have an healthy skepticism. But again, this is a cheap part. My bench is isolated, worst case scenario. I have some smoke on my bench. I have a bunch of these. I didn't pay a lot of money for them. I'm okay with doing it. Okay, so let's just go through how it ran through the plan. And then I'm going to show you the final report. So if you see over here, so I ran this in Claude Code. I did not run this in Cursor. I ran this with Opus 4.6 in max effort mode, 1 million contacts. So this is basically the creme de la creme, absolute flagship model. Now, do you have to do this? Like, this can be really expensive if you don't have a Claude Code a subscription. I do. I have. So I didn't have a problem running this. Obviously, whatever, take it with a grain of salt, run it the way that you want to run it. If you're concerned about tokens, maybe monitor it a little bit more, whatever. I mean, to each their own. I wanted to just go all in with the highest model possible. So it runs through this procedure. And again, running through the procedure, it's like pretty meticulous. So you can have a lighter weight model doing that. It runs through all this procedure, all the tool calls, as you can see here. And this is, again, why MCP is so important, because it's super bounded. It's not like, oh, here's some like ambiguous skill to like, this is how you might turn on an instrument. Or this is like, as you can see, I'm a little bit kind of skeptical about skills versus MCPs, even though people say MCPs are dead. But this is like really deterministic. I know exactly the data in is going to result in data out, and anything outside of that window is just going to fail. I can bound that at the MCP checking. I don't have to worry about my actual like implementation drivers to do that checking. Meaning if a skill calls the Python drivers, like maybe I didn't have proper exception handling, but if my MCP server is being called, then at the MCP server, I can say, no, this was the absolute maximum in the MCP input. And it'll respond right away to the LLM, hey, you can't set an OCP of 5 volts or whatever it is, 5 amps. So anyways, some of that's a little bit of a digression, but that's kind of an important aspect. So we go through all these MCP2 calls. Finally, after it does that, it loads the result summary. So this is the complete sweep of the electronic load running the current sync operation between 0 to 2.5 amps. The V in, the V out, the current in, the current out, and then the power, the efficiency, and then the ripple that we were able to see. So that's kind of super duper nice. I remember back in the early days when I used to work on board bring up, we would literally run this table that you see here with a buddy manually, one by one, kind of like looking through it on a scope, and your power in, power out. Later, of course, we did automate this, but still, it took time to write this loop, and then make sure the loop is good, and then like you did all this automation, but it was just for design verification bring up, and then after that, you've classified your power converter, and then you're done. It's like, well, I wrote all of those automated scripts, I never get to use them again. So this is nice because like there is no automated script. The AI agent just basically runs the MCP in the loop. Okay, so now what we have is these key findings. So it says, okay, Amazon claims product description 0.5% for the load regulation. This isn't fair because I have a long wire, so I'm getting a cable drop. So this is a non-claim. This is false. The peak efficiency, again, I can see some of that loss over the cables. I could see that they classified everything with literally like test probes, like a bed and nail setup. And so you could get really tight voltage, like minimize the voltage drop. But there's no way that like from 67.2% with like test probes, you're going to get 92%. So hard to believe that claim of the peak efficiency at 92% to 73.3%. I mean, that's kind of a squeeze. I could retest this with probing directly on, getting super, super tight between my power supply and my E-load and the actual board. That would be really hard. I'd have to get everything really, really close together. So, okay, take it with a grain of salt, give them 10% margin, 20% margin. The test 3, so again, we're going according to that original plan. So in that plan, we had this different phases of test. So test 3, line regulation. So in line regulation, we have over here, let's scroll back down. It's running this line regulation, and then it'll eventually report everything. So, okay, line regulation results. So VIN, 6 volts all the way up to 25 volts. And then you can see the V out. Again, we do have loss with the long cable that I have. So not 100% fair to say they did a bad job with their design. Let's give them a little benefit of the doubt. Now, the best part, the report. So then it generates the report in that exact markdown format that we requested. And then we have the best part that I love about LLMs, the executive summary, because TLDR, too long didn't read. This module is built around a counterfeit IC. Okay, again, it thinks we're using a TI IC. So it's like not really fair. Like I didn't give it the context and say, hey, like I just bought this, it's not, we can't claim that this is a TI IC. This is their version of LM2596, okay, just to be fair. And then, it says like the thing about the 65 kilohertz versus 150, that is fair, like, but that's clear in the product description. And then here's all the results and then the final report. Super cool. I think it's still really useful. Great for a DVT if you want to bring up a board, design verification testing, comparing components. If you get a spec from a vendor for an eval board or a little kit or a DC to DC in this case, and they do claim certain things and they give you the exact test setup in which they set everything up, could be interesting to run that with an LLM instead of you spending hours trying to replicate that manually. So this was just kind of an insight. It's a basic DC to DC converter, but it really demonstrates like how far we've come with agentic capabilities, especially when you give it the right tools and the right context. So I wanted to take a pause and just make sure that everything was set up, everything is safe. So I have my device under test totally isolated on a lab bench. There's nothing connected. I am going to be setting over voltage protection, over current protection. I'm going to try and be as safe as possible. Ideally, you would kind of want to walk through this manually, step by step. Maybe your MCP tool, like we've talked about in the past, to set barriers or to set ways where it can auto detect issues and then kind of like stop everything. But I'm in a safe state, so I'm going to proceed. So let's look at the plan that it provides. So confirm the dot powers up, setup. Okay, this is the setup that it pulled from my README, which is good. And it says no load power on, do an output voltage check, light load, mid load, and then switching visible. So you want to see that the switching frequency is there, and then shut down. Okay, so yes. Okay, so it's going to now do all of the different tool calls, and we can watch it in real time. Run that. And then maybe we'll have it check out the ripple current a little bit. I'm a little bit skeptical because we are running Sonnet at medium effort. So this type of stuff, it could do pretty easily because it's like step by step, do this, do that, do that. Once you start doing things like trying to process data points, waveforms, extractions, doing FFTs, that's going to be a little bit more difficult. And so I don't have a high level of confidence. I may try this again with a higher model, but let's take a look. So it's going, measuring, running. So as you can see, it interjects in between each tool call and tells us what, we're at this step, that step, all of that. So it's looking at the waveform. So let's go look. Okay, so it's out of range. You can't really see it, but it did run something. Let's go back, see what it does. Disable input, set output state to off. Okay, great. So scope probes appear disconnected. I don't think that's true. I think it had trouble with the ripple current, which we probably need to put it into a higher reasoning model. So I think I will have to use a higher reasoning model in order to check out the ripple current. So today we looked at taking a DC to DC converter, hooking it up to all of my instrument in my lab, but most importantly, an agent did the board bring up itself and profiled it against what it expected to be with the TI specs of the datasheet and the specs of the product description itself in the product description on the website where I purchased the actual device. If you enjoyed this video, please check out the rest of the videos in this channel. Hit that subscribe button so you don't miss a beat, and definitely hit that like button. Thanks for watching.